Okay, thank you. So first of all, thank you to the organizers, of course, for hosting this nice conference and inviting me to speak, and for all of you for coming after what I gather was a late night for some of you. So as introduced, I'm going to speak about the dynamical André-Oort conjecture, but I want to start with some classical motivation of this problem, which is, of course, the standard or classical André-Oort conjecture. And I don't particularly want to get into full generality, so what I'm going to talk about is sort of the easiest to state case of the classical André-Oort conjecture. So what does this conjecture say? Well, via the J function, we can consider the complex plane as a parameter space. By the way, is this visible in the back? Yes? OK. As a parameter space for isomorphism classes of elliptic curves. OK, and inside of, oh, I'm losing my microphone already. OK. And inside of this space, we have particular J invariants, which correspond to elliptic curves with complex multiplication. So recall that that an elliptic curve has complex multiplication. I think this has already been spoken about, of course, which in the elliptic curve case simply means that the endomorphism ring of the elliptic curve properly contains the integers. And so one sort of natural question that we could ask is, what do, in this parameter space, what do the J invariants of complex multiplication points look like? Okay? And in particular, we might be interested in the geometry of these things. Well, if you're talking about Zariski geometry, this is a one-parameter family, and so the only question you can ask is about whether this collection of points is finite or infinite, right? So a few facts for comparison later. Maybe can you come help with this thing? Is it possible? Well, OK, anyways. So a few facts for later. So first of all, there exist infinitely many CMJ invariants. OK. A second fact, which is a theorem due to Schneider, is that an element of the upper half plane corresponds to a curve with complex multiplication if and only if both tau and its image under the J function are algebraic. OK? And additionally, thank you. I'm totally falling here. Sorry.
Just a technical problem. It's okay?
Oh, we'll see, I guess. Is it possible to sort of... This was predictable, right? Yeah. OK, anyways, I'll keep talking. So, so if and only if tau and J of tau are both algebraic, and equivalently, tau is a quadratic imaginary. OK. A few more facts just for analogy. So secondly, the collection of CMJ invariants over a given number field. So over a fixed number field K is finite. But I want to point out that this is not a Northcott property. So in other words, the collection of complex multiplication J invariants is not a set of bounded height, where recall here, by height I mean just the measure of the arithmetic complexity. How long does it take you to write down the minimal polynomial of the number? So they're not a set of bounded height, but nonetheless they satisfy this finiteness property. Okay, so I claimed that I was interested in the geometry of these things, but that in the one parameter setting this isn't so interesting to ask. So let's instead consider a two-parameter space. The easiest one we can build up in this situation is to consider instead C cross C to parameterize pairs of elliptic curves. Okay. In this setting again, sorry, this is a 0. In this setting again, this collection will be Zariski dense in the parameter space. So CM, J invariants are Zariski dense in the parameter space. What do I mean by a CMJ invariant in this case? So let's make a definition. In this setting, we call a point, say, AB special if A is J of tau and B is J of tau prime are both J invariants of CM curves. Okay, so more properly, let's say special points are Zariski dense in this space. Okay, and so then we can ask about the geometry of these things in the following way. Inside of this affine plane, which curves contain infinitely many, or a Zariski dense set of CM, or special points, rather. Okay, so question. Which affine curves contain a Zariski dense subset of special points? Well, okay, there's a couple of obvious ones, right? We have this two-dimensional parameter space comes equipped with the projection maps to the coordinates, say pi1, pi2. If we have a projection, or rather, sorry, if we take a CM point, a CMJ invariant down here, and look at the fiber over that point by one of these two projections, then for sure we will get a curve that has infinitely many CM points. So the first obvious type of curve are fibers over CM. And the second kind of obvious thing, at least, well, you might hope that it gives you an algebraic curve in this setting, is if we look at this statement here, we could ask something like the following. If we want to cook up a curve that has the property that has infinitely many special points, one way to do that is to say, OK, let's forget C cross C and come back to H cross H, right? So the product of the J map gives me a map like this. How can we require that 2 points, tau and tau prime, on a curve are simultaneously quadratic imaginaries, no matter which quadratic imaginary field we're taking here? Well, the easiest way to do that is to just require that, say, for example, tau prime is an integer multiple of tau. Okay? So these descend under J cross J to the 0 loci of modular polynomials. And so this will give you, for each positive integer n, a collection of a particular curve which contains infinitely many special points. Okay. So in some sense, both of these are obvious examples once you know something about the J function, and then of course the fiber, is obvious to everyone. Okay. So the conjecture, which is a theorem, which, as I'm going to state, it is due to André, but generalized to n tuples. So instead of just 2 tuples, by Pila, although of course you'd have to write the statement differently in that setting. But the two-tuple case is due to André is the following statement, that the only curves that can contain an infinite set of CM points, or special points, are exactly the ones that you can obviously think of. Okay? So type A and B, let's be a little more precise here. So C is irreducible. Plane curve contains a Zariski-dense subset special points if and only if C is of type A or B. Okay. And so I wanted to go through all this, although I know it's review for many of you, because I want to point out that when I move to the dynamical setting, essentially all of these things will have analogies. And so I don't want to spend a lot of time on the details of how this is proved, but I do want to make a remark that the key point is that you use this J map, J cross J, to suppose you have a curve that does have infinitely many special points that is not of type A or B. Then you can construct an object that has properties of both a transcendental thing, in the sense that it doesn't have too many points of defined over a number field of bounded degree, but then also has algebraic properties in that it has too many points that are defined over a number field of bounded degree. And so this play of algebraic versus transcendental is sort of crucial to the proof of this theorem, and it will be in the dynamical setting as well. Okay. All right. Any questions so far? Okay. Then let's move to the dynamical setting. Okay. So again, it's a bit easier in this situation, although I will, if there's time, talk about the general dynamical André-Oort conjecture. It's a bit easier to state or predict a conjecture for the dynamical setting in this basic kind of case of a particular family. So what might I mean by this? So first of all, the dynamical setting that I'm considering is the following. So let, say, f of z be a rational map, by which I just mean a quotient of polynomials. So viewed as a map of the Riemann sphere, or a morphism of P1. Over the complex numbers. Okay, so this is the basic object of study. To make things interesting, so when I say I'm interested in dynamical behavior, what I mean is that I'm interested in behavior under iteration by a map like this. Now, that behavior is not so interesting at all if the degree of this thing is 1, if we take an automorphism. So we're going to restrict our attention to degree of f being at least 2. Okay. So before I can talk about what the right kind of analog of the André-Oort conjecture might be for moduli spaces of these kinds of things, I need to give some definitions that are basic to dynamics. So definitions. So the main thing we're interested in here, given a particular rational map, is if we take a point in the Riemann sphere here, and we start iterating that point, we obtain a sequence known as the orbit, or the forward orbit, of that point. Okay? The point is said to be pre-periodic. If the orbit is finite. If the orbit is finite, what that means is that eventually this sequence has two elements that coincide, right? So eventually we land in some cycle. If the point itself is in that cycle, we say that it's periodic. So z is periodic. Sorry, this is a bit low. If, say, fn of z equals z for some n greater than or equal to 1. Okay? So z coincides with some forward iterate of itself under the map f. All right. The other sort of objects that we need to consider in this setting, so more definitions, and then I'll just look at a simple example. So in particular here, so if we have a rational map and I want to understand what happens to the points under iteration, then there's sort of two possible behaviors that can occur. Either I start at a point, and whatever happens to it under iteration happens on a small neighborhood of that point, okay, or not. All right, so accordingly, we define the Fatou set of f of f, to be the collection of points in the Riemann sphere such that behavior under iteration is stable on a neighborhood of the point. And the unstable locus is known as the Julia set. Sorry. Or the complement of the Fatou set. Okay? So as an easy example, as about the only easy example, consider the power map, z to the d, where d is at least 2. Now, if we look at the points on the Riemann sphere and ask what happens under iteration by this map, well, the nth iterative of this map actually has a closed form, right? So if we start taking powers by d here, the nth iterative of this map will simply take the d to the nth power of a point z. So what is happening here is if we start with a z that has modulus that's smaller than 1 in the complex plane, when we iterate it, we're going to get things that have smaller and smaller modulus. In other words, this thing is going to go to 0 under iteration, okay? So if modulus of z is less than 1, then the orbit of z converges to 0. Conversely, if we have modulus greater than 1, then the orbit of z converges to infinity. All right? So in particular, both of these are open sets, right? And so these are necessarily part of the Fatou set. Okay? It turns out that these are the entirety of the Fatou set, and that's basically immediate looking at this. If you take some z that lies on the unit circle, any neighborhood of that thing will contain points that go to 0 and points that go to infinity. Okay? So this locus is necessarily unstable. So the Julia set in this case is simply the unit circle. Okay? All right. But you can almost never write it down like this, right? This is sort of an exceptional case, so don't be misled by that. But it's a good illustration of what I mean by stable and unstable loci. Okay. All right, so let's talk about now dynamical moduli space. Are there any questions about these things? No? Okay. All right, so again, rather than talk about the full moduli space of rational maps of degree d, I'm going to restrict my attention as I did in the classical setting here. Okay? So the first thing to point out is that there's a notion of equivalence of two dynamical maps. So f and g are equivalent. Well, what might I want this to mean? I want this to mean that their dynamics are equivalent, essentially, right? The way that this could happen is if I have some transformation between them that respects the process of iteration. And that's exactly conjugation by some automorphism of P1. So if f is, say, mu inverse composed with g, composed with mu, where mu is any Mobius transformation, so, or rather, an automorphism of P1. Okay? So in particular, this is probably something that almost everyone is familiar with here. If we want to make some restriction on f, say, consider polynomial dynamics, then if degree of f is equal to 2, there's only a one-parameter family of these. So the collection polynomial maps of degree 2 has dimension 1. And you can see simply by making a conjugation by an affine transformation that such a thing can be written as z squared plus c. And these things are not equivalent. And so in other words, C is a parameter space, is the parameter space. for such maps. Up to equivalence. That's right. Up to equivalence, yeah. I'm always considering things in the collection of rational maps modulo automorphisms of P1. Yes. OK. Maybe I want to leave these things. OK, so just as in the classical setting, I have this line which parameterizes dynamical systems rather than elliptic curves or equivalence classes of such. And it turns out that there actually is an analog of complex multiplication that's relatively natural in this setting. So let me make one more definition and then try and convince you that this is a reasonable analog. Okay? So we say that a map f of z is post-critically finite if all critical points of f are pre-periodic. Okay. Now, this might sound a little bit arbitrary if you're not familiar with working with complex dynamics, but in many ways, the dynamics of a map like this is controlled by its critical points behavior. So a simple example is the following, okay? If all critical points are periodic, let me say this. In the family z squared plus c, you can tell whether or not the Julia set is connected simply by considering the orbit of 0. If the orbit of 0, which is the critical point in this family, if the orbit of 0 is bounded under iteration, the Julia set will be connected. If it's not bounded under iteration, the Julia set will not be connected. Okay? Oh, critical, I really just mean ramified. So it maps to its image with degree greater than 1. Yeah. OK. So in the example of the family over here, just the point 0 and the point infinity, technically, but this is a fixed point. OK, so this isn't as arbitrary as it sounds, because in many ways, the dynamics of the map is controlled by the critical points. And so we have this collection of maps which lie somewhere in my space, in my parameter space. And so a couple of things to point out about post-critically finite points, which, by the way, I'll often abbreviate PCF. So some facts about PCF points. First fact is there's infinitely many of them. OK. Second fact is they're all algebraic. OK. This is relatively easy to see, right? What does it mean for a map of this form, at least? Let's restrict our attention to these maps. What does it mean for a map like this to be PCF? Well, it has two critical points, one at 0, one at infinity. Infinity is fixed. 0 is pre-periodic. All that means is that you're finding some forward iterates of 0 under this map that are equal to each other. In other words, a polynomial in C. Okay? So these things are algebraic. Secondly, they also have a finite property. So the set of points that are PCF defined over a given number field, defined over, is finite. Okay, but this is a Northcott property. Okay, so the set of PCF points, and actually this takes quite a bit of work to show in general, but it's easy to show in this family. The set of PCF points is actually a collection of points of bounded height. All right? OK. You can make this definition for the entire family of rational maps up to modulo equivalence, and all of these facts will still be true, but they're much more obvious for this family, and I'm going to focus on that in a second. OK. All right, so I do want to say, well, I'll just say this out loud for purposes of time. Yes?
So, but you said that it is not property, but you don't know the degree of the polynomial that it's going to algebra. You only know that.
In this family, you can compute the degree of a PCF map with a particular requirement, but they will certainly be unbounded degree. But the height can still be bounded, right? Because when we consider the height function, we sort of normalize by the degree of the extension, right? Okay. All right. So there is one sort of much more convincing reason why these are analogous to CM points, but it's a little complicated, so I'm just going to say it out loud for those of you who are familiar with this. So to an elliptic curve, you can associate a representation, a Galois representation known as the L-adic representation. And it's a theorem of Serre that this representation will have large image in the sense of finite index image, if and only if the elliptic curve does not have complex multiplication. Okay? Accordingly, to a dynamical system, you can associate a Galois representation of a tree, which you get by taking a certain pre-image of a point under the dynamical system. You get a Galois representation, which maps into the automorphism group of this tree. That representation, it's not quite true that it has finite index if and only if the point is not post-critically finite parameter, but it's almost true. Okay? So work of mostly Pink and Jones gives a more convincing analogy. Okay, but it's a little technical, so let's skip it. Okay. All right. So my claim here, and I left these things up here, of course, for this particular purpose, is that PCF points are actually analogous to CM points. And so you could certainly at least make the same conjecture that you did for elliptic curves. Now, maybe it's true, maybe it's not. But we can write it down. So this is a case of dynamical André-Oort. And that is, you could conjecture that if we consider products, so pairs of rational maps that are polynomials of degree 2. So now I'm restricting my attention to this family here. So consider the affine 2 spaces parametrizing pairs of these things. And call a point special in this space if both coordinates are PCF parameters. Okay. Well, so when we formulated the original André-Oort conjecture, there were some obvious curves. We want to ask which curves contain an infinite subset of special points. There were some obvious examples in the classical setting. Again, there are some obvious examples here. So our type A from before will still be an obvious curve with infinitely many PCF maps, right? So if we have a curve, so say C is an irreducible algebraic curve in this affine 2 space, well, again, we come equipped with projection maps. And if we look at the fiber over a projection of a CM point, sorry, I want the full space, but yeah. If we look at the fiber over a PCF map of one of these 2 projections, then of course we're going to get a full copy of this family, and so we have infinitely many special points. Okay, so fibers over pi I. Fibers under pi I over PCF points. The second type of curve that you might get, well, what did we do for the modular curve, or the modular polynomials? We said that how can we come up with a relation between 2 parameters that will guarantee that when one of them is CM, the other one is also CM? Okay, so how can we come up with a relation that will guarantee that if A is a PCF map, if Z squared plus A is a PCF map, then Z squared plus B is a PCF map? Well, here's the thing, is that you really can't, okay? So in the Z squared plus C family, well, okay, you can if you take the diagonal. Right, so if C is equal to the diagonal, this will do. But other than that, there is no way to guarantee that you get this kind of behavior, okay? So to illustrate that, let me sort of make a comment here. So the PCF parameters their complex geometry, if you look at them in the complex plane, is also interesting. So let's make another definition here. So define the bifurcation locus. First let's define the stable locus of the family of maps fc of z is z squared plus c, is the set of parameters c such that on a neighborhood of c, the map which takes a parameter to the Julia set of its associated rational map is continuous. And the topology on the right-hand side here is the Hausdorff topology. Okay? So this is a moduli space sort of version of, I think I erased it, of the Fa2 set, right? So what I'm saying is that I have a parameter c that if I perturb this parameter c by a little bit, then the dynamics of the maps near C will be similar to the dynamics at z squared plus c. Okay? And the bifurcation locus is the complement of, sorry, I didn't write down the name here. Call this thing, say, B of the family. The bifurcation locus is the unstable locus in moduli space. In other words, when I perturb my parameter c a little bit, the dynamics changes dramatically. Okay? Now, in this family, we can write down this thing, well, somewhat. Yes, thank you. Otherwise, very poor notation, right? Yeah, at least for English speakers. Okay, so the Hausdorff topology. So continuous in the Hausdorff topology, meaning, you can really think of it as like the Julia set is continuously deforming on this neighborhood. So it's equivalent to say that this is a holomorphic movement. The Julia sets move analytically. But I don't know if that helps. But okay. So what is the bifurcation locus of this family, by the way? So fact, the bifurcation locus of the family z squared plus c is the boundary of the Mandelbrot set. Okay, so what is the Mandelbrot set? If you recall, I said that there was a dichotomy in the shape of the connectedness of the Julia set that depended on whether the critical orbit of a polynomial was bounded or not. Okay? The Mandelbrot set is defined exactly this way. It's the collection of parameters such that the critical orbit is bounded, or equivalently, the Julia set is connected. Okay? So what does this thing look like? So I didn't even bother putting a picture on a slide because we've all seen pictures. So this is this sort of complicated guy. And you can tell that it's complicated because of my little tendrils here. So the Mandelbrot set lies inside the complex plane. It's this collection of parameters under which the critical orbit is bounded. Now, by definition here, if I'm requiring the critical orbit to be bounded, any PCF map in this family will necessarily be in the Mandelbrot set because a PCF map has critical orbit that's actually pre-periodic, right? So the PCF parameters are inside of the Mandelbrot set here. And in fact, there's some isolated PCF parameters in components of the Mandelbrot set, but most of them lie on the boundary, and they form a dense subset of the boundary. Okay? So another fact, and this is general for bifurcation loci, is that PCF parameters form a dense subset of the boundary. In other words, of the bifurcation loci, of locus, rather. Okay, now, why have I gone through all of this trouble? Well, so what would it mean if I could cook up a special curve of the other type? It would mean that I had some requirement that whenever C was PCF, that C prime was PCF as well. And what that would mean is that I would have some correspondence here on the boundary of the Mandelbrot set that would take PCF parameters on the boundary to other PCF parameters on the boundary. And so my claim is that, and I'll get into the details here with time, so my claim is that the way that one should go about proving this thing is, in the roughest possible way, analogous to the classical setting, which is that you should use these two things to cook up an object which simultaneously has transcendental properties and algebraic properties. And that thing should be this bifurcation locus. Okay? So, let's see here. So let's finish writing the conjecture that I sort of abandoned over there. Okay. So, in fact, let's rewrite it because this is now a theorem. With my co-authors, Dragos Ghioca, Nguyen, and Heshu Yi, which is that if C is an irreducible plane curve with infinitely many special points in the sense of dynamics, so PCF special points, then C is of type A or B. C is of type A or B. Okay. So the only curves in this plane which contain infinitely many points, which consist of two post-critically finite parameters, are the obvious ones: fibers over PCF points under the projection map and the diagonal. Okay? All right. So, is this okay for everyone? Yeah. All right, so let me give you an idea of how you go about proving this. So sort of the program of proving these kind of things was developed by Baker-DeMarco. So methods in general here for the strategy of the proof is due to Baker-DeMarco. And it, again, as with the classical case, consists of two components. Okay? So first, so I claimed that the bifurcation locus, that the boundary of the Mandelbrot set, somehow, if we have a plane curve here that has infinitely many special points and is not of type A or B, will have properties that are both transcendental and algebraic. Okay? So the first part is the algebraic part. So the first step is to show that such a curve, if C has infinitely many special points, then membership in C induces an algebraic correspondence on the boundary of the Mandelbrot set. Okay? I'm sorry? The special points are a dense subset of the boundary. That's right. And so, yeah, but this is actually a bit complicated to show. So what are you saying here, really? What I'm saying is that you can go from the assumption that you have infinitely many special points on the curve to deducing that, in fact, for every pair on the curve, z squared plus a is PCF, if and only if z squared plus b is PCF. Okay? So this is actually a very nice theory, and it's a little bit delicate and not what I want to talk about. But I will say the main tool here is an equidistribution theorem of points of small dynamical height in full generality. There's a nice version of this equidistribution theorem due to Nguyen. But in the one-dimensional case, such as we have here, there's various proofs of this due to Chamberlain, Baker-Rumley, etc. Okay. All right. But what I want to talk about with my remaining time here is the second part of this proof, which is that the boundary of the Mandelbrot set is too transcendental for such a correspondence to exist. The correspondence depends on the curve C. So z squared plus a corresponds to z squared plus b if and only if ab is a point on that curve. Yeah. Yeah, sorry, I wrote this a little bit poorly. Yeah. But OK. So step 2, no such correspondence exists. And all right, so there's a lot of reasons why you should think that this is true, okay? So let me just outline one sort of verbally. So the boundary of the Mandelbrot set contains a lot of data about the points that it parametrizes in the following sense. If you take a PCF point which lies on the boundary of the Mandelbrot set and you zoom in on the boundary of the Mandelbrot set there, what you will get will look just like, and again here I mean continuous in the sense of the Hausdorff topology, will look just like the associated Julia set of that PCF point. Okay? So roughly speaking, the boundary of the Mandelbrot set encodes the dynamics of infinitely many parameters, of every single PCF parameter on its boundary. Okay? And since there's no algebraic relation between the Julia, well, okay, this is, again, roughly speaking, since there shouldn't be algebraic relations between the Julia sets of the various PCF parameters, there shouldn't be a way to go from one element on the boundary of the Mandelbrot set to another in an algebraic way. Okay, so that's sort of the moral reason why this should hold. Now, how do you actually prove this? Yes, yes. I mean, so these Julia sets in general will be like very complicated fractals, right? So of course we had the example of a circle, but there's a very exceptional example. So in general, for example, the Julia set of something like z squared plus I will be this very spindly fractal guy. Maybe this isn't the most helpful illustration, but in any case, yes, the Julia sets themselves are very, very transcendental in some sense. Okay. Okay, so let me sort of outline. There's a really nice proof of this in the case where C is defined as the zero locus of a polynomial. So suppose that C is cut out by some polynomial. Okay. It turns out that you can show in this case that if C is cut out by a polynomial, then because the boundary of the Mandelbrot set will be invariant under this polynomial, it's actually not hard to show that the Julia set of this polynomial is equal to the boundary of the Mandelbrot set. Okay? All right. And this should never happen. So let me give you an idea why. So inside of the Mandelbrot set, we have these particular components, which actually have these nice semi-algebraic boundaries, right? So the main component, this large component, is actually a cardioid. So in particular, there exists a map. Here's what it is. Mapping the unit circle into the boundary of the Mandelbrot set, which simply takes the unit circle to the boundary of this main cardioid that appears. Okay? Now, if we say that we have a polynomial whose Julia set is equal to the boundary of the Mandelbrot set, well, the boundary of components like this in the Fa2 set So this component of the Mandelbrot set will be a component of the Fatou set of the polynomial P. And it's a theorem due to Sullivan. This is known as Sullivan's no wandering domains theorem. That then there exist iterates, say n and m. Let's give this a name. Let's call this component, say, h. Okay? There exist iterates n and m so that the image of h under these two iterates coincides. N not equal to n here. Okay. So in other words, let me also give this a name, say R of z. In other words, there exist polynomials, say big F and big G. I'm just defining these things to be iterates of P composed with R, such that F of G of S1 is equal to G of S1. Okay? Now, it's a composition of a power of an iterative P with R. Yeah. Okay. All right, so now I claim that work of Medvedev-Scanlon guarantees that this thing can't exist. Okay? So why can't a circle satisfy this kind of polynomial relation unless G is very special? Well, there's a way to embed this circle inside of a curve, say D. Let's use affine space here, say A cross A, which takes a point Z that lies on the unit circle and maps it to ZZ bar. And the curve D here is going to be cut out by the relation xy equals 1 in affine 2 space. Okay? So every point on the unit circle will land in a point on this curve, which is inside this plane, which sits inside of P1 cross P1. Okay? And this relation guarantees that if we apply the product of this map F to the image of D, so let's say G cross G of D, invariant. Okay? So we use the fact that we have a polynomial relation on the unit circle to cook up an invariant curve in P1 cross P1 under a product of a polynomial with itself. Okay? And by work of Alice and Tom, this forces that map G to be exceptional. And without defining what exceptional means, this forces G, and in particular, means that the Julia set of G is very simple, the dynamics of G is very simple, and forces the boundary of the Mandelbrot set cannot then be the Julia set of the polynomial that I started with, which I called P. Okay? So finished. Okay. So a couple of remarks about generalization. So first of all, in the case of, this is a very special case of a curve, right? So I have a rational curve here cut out by y equals p of x. This argument won't go through in other cases, in particular because the classification of invariant curves over here, even if we replace p by a rational map, is not as well understood. Okay? But then additionally, if we don't have a rational curve here, this argument, there's no Julia set in play here, and so it's not even clear how this should work. And so the way that this is actually proved, this complex part of this thing was proved by us, is actually a complex dynamical argument instead of invariant curve argument. However, there's some hope of sort of expanding these things, at least for polynomials. So maybe a final remark here. Everything that I said in this conjecture can be applied to general spaces of dynamical systems. So let me sort of loosely say a general dynamical André-Oort conjecture roughly says something like the following. So if V is an algebraic family of rational maps, with a Zariski dense subset of post-critically finite points, then the conjecture should be essentially what I said about the diagonal being a special curve here. So it should be something like, then V is cut out by forcing some relation on the critical points. Okay? So by critical orbit relations. In other words, things of the form say, one critical point is equal to the second iterate of another critical point. This is an example of what I mean by a critical orbit relation. Or something like a fiber over a PCF point is forcing the critical orbit relation, which exactly cuts out that PCF point. Okay? So this is a conjecture, and it has some hope. And the reason why it has some hope is, well, first of all, this equidistribution theorem, there is a version for higher dimensional varieties. You can't just use Zariski density. It's a little bit more complicated than that. But if one could get to this theorem, if one could cook up something that satisfies the hypotheses of that equidistribution theorem, that's actually in place. The second thing is that the Mandelbrot set, now in general, PCF points, the transcendental object I want to construct will be the bifurcation locus of the family, which doesn't necessarily have anything to do with the Mandelbrot set anymore. Okay? But there's a theorem due to McMullen that says that actually the Mandelbrot set is universal in bifurcation loci in the following sense. Every non-empty bifurcation locus contains quasi-conformal copies of the Mandelbrot set. Or you can generalize the Mandelbrot set here by replacing z squared plus c with z to the d plus c. I'll just call that the d Mandelbrot set. So quasi-conformal here just means that locally what this map does to small circles is stretches it into ellipses with bounded eccentricity. Okay? So the methods that work for the Mandelbrot set actually have a hope of working in general for any bifurcation locus. And so it's possible that this dynamical André-Oort conjecture is a little bit more feasible to be completely solved than in the classical case. Okay? And I should stop there.